Mercury's equator routinely reaches temperatures of 800 degrees Fahrenheit, yet sitting directly on that same planet is water ice, frozen solid. The first hint of this anomaly appeared in 1991. Astronomers using the Arecibo radio telescope in Puerto Rico bounced radar signals off Mercury, expecting the dull return of bare rock. Instead, near both poles, they received highly reflective signals back, a signature perfectly matching frozen water. The problem was, nobody could verify what those bright patches actually were. Up to that point, humanity's only close-up look at Mercury came from a brief spacecraft flyby in 1974, which mapped less than half the surface. We had no complete map of the poles to compare the radar data against. The hottest planet in our solar system was broadcasting a signal that directly contradicted its nature, and we lacked the evidence to figure out why. You might wonder why it took decades to go back and check. Over the course of a year, Mercury is, on average, the closest planet to Earth. Venus and Mars are further away, yet they received dozens of visitors, while Mercury sat unvisited for 30 years. Falling into the sun's steep gravity well, a spacecraft constantly accelerates. Reaching Mercury, you travel 30 miles per second. Braking to match its speed exactly requires so much propellant that a 1970s spacecraft would have zero room for scientific instruments. By the engineering standards of the time, Mercury was effectively unreachable. Stopping there required more energy than leaving the solar system altogether. In 1985, a trajectory specialist at the Jet Propulsion Laboratory named Chin Wan-yen figured out a loophole. Instead of carrying massive amounts of fuel to hit the brakes, a spacecraft could use planets to slow itself down. By passing a planet on the correct side, you can strategically give up a small amount of orbital energy, slowing your speed relative to the sun. Look at the orbital map for the mission NASA eventually built around her math. To cross a distance of 48 million miles, the Messenger spacecraft took a 6.5-year detour spanning nearly 5 billion miles. It required 1 flyby of Earth, 2 of Venus, and 3 of Mercury itself, shedding speed little by little across the years. Messenger launched in 2004, carrying enough propellant to make the trip, but its most critical defense mechanism was entirely passive. To survive sunlight 10 times more intense than what we experience on Earth, the instruments hid behind a heat-resistant ceramic sunshade for the entire journey. The team even found a way to use the intense environment to their advantage. By precisely angling the spacecraft's solar panels, they caught the physical pressure of the sunlight itself, using it as a gentle, continuous brake to save even more propellant over the years. They abandoned a direct flight path for a multi-billion-mile endurance marathon, solely to bypass the rigid limits of rocket propulsion. In March 2011, Messenger finally fired its main engine and slipped into orbit. Because a low pass over the sun-baked rock would literally cook the spacecraft from below, engineers put it in a lopsided orbit, dipping close to the surface for brief observations, and then retreating thousands of miles out into space to cool down.
Over the poles, the science team targeted 3 distinct instruments. A neutron spectrometer searched for the chemical signature of hydrogen, a laser altimeter bounced light off the ground to measure reflectivity, and a thermal model calculated the exact heat radiating off the rock. Building momentum. The results aligned perfectly. The areas with the highest hydrogen concentrations and the brightest reflectivity were sitting in the exact craters the models predicted would be the coldest. 21 years after Arecibo detected that bright radar signature, the data was conclusive. The solar system's innermost furnace was hiding deposits of solid water ice, several feet thick, tucked away in the permanent dark. Earth tilts 23 degrees, bathing our poles in sunlight. Mercury barely leans at all. Its poles never tip into sunlight. Compounding this, Mercury has no atmosphere to scatter heat into the shade. Inside its deep polar craters, the shadows are absolute. This creates cold traps. These deep crater floors sit just a few feet away from rock hot enough to melt lead, yet they have not received a single photon of sunlight since they were carved. They remain colder than the surface of Pluto. The exact planetary geometry that forces Mercury's equator to absorb relentless solar radiation is the precise mechanism that turns its poles into a permanent freezer.
But the closer Messenger looked, the stranger the data became. Across most of the polar deposits, the ice wasn't exposed. It was buried under a thin crust of exceptionally dark material. When analyzed, its properties matched organic, carbon-rich compounds. Since Mercury does not generate carbon, the leading explanation traces back outward into space. For 4 billion years, water-rich asteroids and comets have been crashing into the inner planets, carrying both water and organic chemistry. When one strikes Mercury, the intense heat instantly vaporizes the payload. But a tiny fraction of that vapor inevitably drifts across the planet and falls into one of the polar cold traps. The moment it touches the pitch-black crater floor, it freezes solid and stays there forever. Messenger mapped this archive for 4 years. By late 2014, with its fuel tanks empty, engineers kept it aloft by venting pressurized helium from its plumbing lines. When that ran out in 2015, the spacecraft plummeted to the surface, crashing permanently into the very terrain it spent a decade trying to reach. Even with a complete map, questions remain. About half of the permanently shadowed ground at the poles shows no icy signature at all. Investigating why these specific craters remain empty is a primary goal for Bepi-Colundo, a joint mission scheduled to enter orbit in November 2026. What they are studying is an untouched vault. Through billions of years of bombardment, the world closest to our sun collected the exact same combination of water and carbon chemistry that rained down onto the early Earth. It is holding on to the raw ingredients of biology, perfectly preserved in the dark.